And it's our guest Dezso Miklos, who will speak on the vertex sign balance of hypergraphs. Probably graphs, probably hypergraphs.
Somehow my slide disappeared.
Disappeared?
Yeah.
Középen.
Oh, yeah.
Listen.
Okay. So, and Choka yesterday mentioned one of the problems he covered in his talk was the by now so-called Miklos-Singhi conjecture or question or whatever. And well, it's not a big wonder that I will start from there, but I will somehow reach to this vertex sign balance, define that for graphs and hypergraphs, which is very much related to this conjecture. And sometimes a little bit later in the talk I will explain this big army of authors who are now appearing, co-authors who are appearing on the blackboard. But maybe first I let me just go and give my view of the Miklos-Singhi conjecture and a little bit of the history of the question. So, Andre somehow approached it from the different sides. He was rather, in the original form of the question was, and there's this one. We are having a bunch of numbers, some of them is positive, and if some of them is positive, then clearly there are a certain number of subsums which are positive. Somehow the k subsums always play an important role. So the question is how many k subsums will be positive, and of course everybody can be positive, but if you have a clever construction, then you can minimize the number of positive k subsums. And as everybody, or at least somebody from the audience guessed yesterday, it's just the opposite what as I said, minimizing. So in this case, you have is one negative number and all the others are positive. So the number of positive, one like Andrea pointed out, one positive number and all the others are negative. So you have to input the positive number among the k numbers, and you get n-1 choose k-1. On the other hand, this is clearly not true if n is less than 2k, because for the small case it's the opposite will work. Then you can have n plus k-1 positive subsums. You take only k-1 positive numbers and one negative number. So to have positive subsums, you have to choose all the subsums for the positive numbers. And if n is less than 2k, then the other construction, the n choose k-1 will be a smaller number of positive subsums. So at this stage, that was the very early stage of the research. There was clearly a similarity to the Erdős-Corrado problem. The answer is the same. There are two different answers when n is less than k or when n is bigger than 2k. So for a very short time, the conjecture was that if n is bigger than 2k, then this n-1 choose k-1 is the best construction. Until I found this counterexample, which also was mentioned yesterday by Andre. So in this case, if k is equal to, if n is equal to 3k plus 1, then there is another way of choosing those numbers. Three negative numbers and all the others are positive. With a properly chosen way, that the sum is positive, but minimize the positive subsums. And in this case, the number of positive subsums is less than n-1 choose k-1. A similar construction works for 3k plus 2, 3k plus 3 for a certain number of about 3k, 3 and then 1/7 k, I believe, check. But so clearly the easiest way to make the conjecture was that the trivial construction, the best construction, is always working if n is at least 1k. What made a little bit also more complicated the picture was that for n is equal to 2k, when the n minus 1 choose k minus 1 and n choose k minus 1 cases are equal to each other, it's very easy to prove that as the minimum number is take a set and the complement of the set, the usual trick will always work. And also, it's not very difficult to find an induction which proves that if for some cases, for some n minus 1 choose k minus 1 is the best construction, then for n plus k the same statement is true. So that it's a simple double counting argument. So therefore, if this is the optimal answer for 2k, then this is the optimal answer for any multiple of k's. So in particular, it's also the optimal answer for 3k. So for 3k, the answer is this one. For 3k plus 1, this doesn't work. And then this was the conjecture made in 1986. We just had to read it. So this is the we made the conjecture at the same time when we had the first upper bound. So the first lower bound on the size of n from which the statement is true, and the first upper bound was, as you see, very bad. And as Bela more or less pointed out yesterday, this problem was completely forgotten for about 25 years, until I gave a lecture at the Bela seminar in Cambridge about probably some other problem that I also mentioned this one, and Misha Tjomkin from the audience got interested in the problem, and I think in a very short time he gave a better bound on the threshold. And then, as Andrea also pointed out yesterday in his talk, very quickly a couple of other papers, quite a few other papers, were published about this problem, and different set of authors were trying to push down the bound. So first, our one is Sudakov put it down to a quadratic bound. The later bound of Peter Frank was a little bit less powerful, but it was a much shorter and simpler proof, so this is why I mentioned it here. But still the question was whether the question is still, probably still a question I am not completely sure about, that if the conjecture is proven or not, but definitely there was a gap between the linear conjecture and the quadratic upper bound. Well, during that, okay, that's coming the next cycle now. So I'm going back a little bit to the Alan Shudakov paper, and they introduced this property, which basically are, they generalized the problem a little bit, so they reformulated the problem, and they, instead of asking for positive, for a set of positive numbers of all the subsets, all the k-element subsets, now they generalize the k-element subset as a hypergraph, the k-element subset as sets of edges of a hypergraph. So the question is, if we are given a hypergraph, and we assign weights to the vertices of the hypergraph, these are the numbers, the sum of them is positive, then the question is, what is the minimum number of the non-negative edges? If you consider the hypergraph to be the complete k-uniform hypergraph, then this is exactly the Miklos thing in question, but any kind of hypergraph, you can ask this question. And we introduced the Miklos single property of the hypergraph if this minimum number is delta of h. It's clear that the minimum number is at least it's clear that you don't. If you consider all the weighting of the edges, and you want to make it in a kind of an optimal way, such that the number of non-negative edges is minimal, then what you you can always reach delta of H because you just, as the original construction, you just assign one big positive number to one vertex. I mean, the vertex is a minimum degree, and all the others are negative. You have to include that vertex. Only the edges by that vertex will have positive edges. So delta of H is the best, the optimal one, and the hypergraph is supposed to have the manicomical property as they defined it. If this is the answer. But basically, the theorem was a little bit stronger than the original manicomical. They proved this property not only about the k-uniform hypergraph, but about a bunch of other hypergraphs having this property. So the hypergraph has to be n-uniform, has to have many edges, has to be r-uniform, so r is now k, has to have many edges, and for every, and it also must have an equal codegree for every pair of vertices, and then they prove that it's true. Clearly, the complete k-uniform hypergraph has equal codegrees, so in particular, this theorem gives a cubic lower bound on the threshold for the validity of the manicomical single conjecture. Well, the question was if equal codegree can be omitted. I mean, equal codegree was definitely an important part of the proof, but the question is if the statement is true for every n, which of course includes the manicomical single question. Now, toward the exact or linear bounds, Bokowski also included this manicomical single property. I'm not sure if they have independently introduced it. They use the same name, which maybe is a good choice, but two different papers more or less independently appealing this definition. And Bokowski proved that the kind of a Katona's averaging or circle permutation type of method, that if there is a hypergraph, irregular k-uniform hypergraph on any vertex which has the manicomical property, then it's also true for the complete k-uniform hypergraph. And he gave a construction of a hypergraph which he needed for the proof, and that worked for a quite big but linear bound on it. So this was the first linear bound for the validity of the manicomical single property, and then a paper has been published by Lilovsky, and now we are in Russia. Maybe somebody knows about this paper. I read quite a few. I mean, I tried to read the paper, and I read quite the demands of quite a few people who tried to read the paper. Nobody understood the paper, so I am not. It's still a kind of a debate if the paper is right or not. My problem was not only that I read the machinery Lilovsky used in the paper, which I could learn, but I was lost completely within the middle of the first page in the definition. I mean, in the notations which were not defined, so I didn't really know what was going on. But in any case, I understood the two theorems which are here. So I mean, these are the two theorems claimed to be proven, and if they are true, then I mean, if the proofs of the theorems are correct, then they completely settle the manicomical single property. The first one. The first one basically reconfirms Endel's conjecture from yesterday. If you were here and you remember, Endel stated that I mean, using the limit version of the problem, he found, and he was quite sure that he was right, and I am also sure that he was right, he found all the constructions which might be the best for different values, different relation of n and k, but all of those constructions were similar, I mean, in the sense that the positive numbers were all equal and the negative numbers were also all equal. So a weaker but still quite strong conjecture is that if you want to minimize the number of positive K subsets, then the best construction always is choose a bunch of positive numbers and a bunch of negative numbers, of course properly weighted, and that's one of them will be the best one. And basically that's the first theorem, this not so beautiful sum form is if you think a little bit about it, is exactly the sum, it is exactly the number of positive subsums if I am not sure there are A positive and N minus A negative or otherwise numbers. You take the number of them and you minimize it for all the possible ways. That should be the number of them. And then, so this was one of his theorem, and the other theorem basically states that if n is bigger than 4k, then this minimum is equal to n minus 1 choose k minus 1, which is the extreme case if a is equal to n minus 1. The second one is a not very, I mean it's a little bit lengthy technical calculation of binomial coefficient. Probably it's true, but the question is, we will leave the first statement of Milovsky's true.
Does the first one say anything about the extremal graph? Or extremal distribution of graph?
Sorry, I don't understand. You mean it's only? I mean that. Or if there are any other examples, you mean?
Yes.
I think no.
Does he prove it?
I don't even know if he proves the same or the same. I mean, as I said, I'm completely lost.
Does he claim it?
Does he claim that the extremal construction is unique? I don't know. As far as I remember, he doesn't. But okay, so then the Miklos thinking property, which was then introduced by Koprovsky and Allen and others, led me to introduce this is the Miklos thinking property, and clearly here what we talk about is the number of non-negative edges. So what is the minimum number of non-negative edges if you have a weight assignment to the vertices with a total sum equals or being positive? The property only considers the case when this minimum number is at least is that of h, but then it's just, as I said, it's just one step to introduce this parameter of a I will use the first part of the talk only graphs, but clearly the same question or the same definition can be introduced for hypergraphs. And now I go back a little bit to the, as you can see at the back of the slide, to this argue of the authors. So what's coming on from now on, this is work which we have been doing with different groups of undergraduate students at Budapest semesters in mathematics, where we do try to offer the different kind of research problems. And once you have a new graph parameter that you know nothing about, it's a good idea to start with the students, because I mean they can find anything. I mean, this is something. This is a research which will definitely give you a success, because in the worst case you can find some trivial statements or something like that. But you can explore that. So the first, this is. This is done, and the first set of the course was where I said all undergraduate students in mathematics. So the vertex sign balance then of the hypergraph, as I just mentioned, is this parameter. You assign all possible all possible weights to the vertices. The sum should be non-negative. And over all the assignments you consider the positive edges, if you take the minimum number of these positive edges. by the previous lemma clearly is bounded above by the minimum degree, and it can be as low as 0. So, I mean, if you cleverly choose, not very cleverly, if you choose like for a pass, for example, if you choose a pass and you clever, almost trivially you assign ways that you can do that such that there is no positive edge at all, even though the overall sum is positive. So here is the first theorem which we found about the vertex sign balance. So the question is, okay, then it can be even 0, but when is it non-trivial? When is it at least 1? And the second, third, and fourth statements of this theorem were of course known to be equivalent earlier, but it's also we have proven that they are equivalent to the case when the vertex sign balance is at least 1. So clearly, if you have a matching of the graph, if you can find a matching in the perfect matching, then the vertex sign balance must be at least 1, because the perfect matching edges will cover all the vertices exactly once. So the sum of the weights of the edges will be the sum of the total sum of the weights. The total sum of the weights is positive, so at least one edge has to have a positive weight. So in that case, a perfect matching implies that the vertex sign balance is at least 1, but perfect matching is completely this is the graph with odd number of vertices. And there are odd number of graphs with odd number of vertices also have a vertex sign balance at least 1, and then it just turned out that the instance of a perfect 2 matching is the equivalent statement to that. I mean, it's not a very difficult theorem, clearly, and the proof is it's not a very big deal. Probably the easiest is to prove the statement, to prove the equivalence of number 1 and number 4. Both cases, basically, what we are doing is we are assigning the weights to the vertices, and with a clever transition of the weights, one of the problem can be translated to the other problem, and then you get that they are equivalent to each other. But then this statement, I mean, this theorem gives us this edge removal lemma, which basically says that this vertex sign balance evil is equal to the minimum number of edges one can remove from a graph, such that the resulting graph will only have a 0 minimum sign balance, and then this lemma is quite trivial, and then the previous theorem, and this lemma together implies that this vertex sign balance is equal to the minimum number of edges covering all perfect 2 matchings of the graph. And then, of course, now, I mean, it gives us a tool to find the vertex sign balance of a graph, because of course the upper bound can always be found by a proper example, but the lower bound of the vertex sign balance can be proven by finding a minimum number, a set of edges covering all perfect 2 matchings, and if the 2 numbers are equal to each other, then we got the vertex sign balance of the graph. So this is why this theorem, which is again relatively easy, turned out to be quite useful, because that helps to find again the vertex sign balance of the graphs. In particular, this theorem, I mean, using this theorem, it's quite easy to find don't know how many 10s or 11s proof of the fact that the Miklos conjecture is proof for graphs. Of course, there are, I mean, that's the simplest case, and many authors prove that, even quite a few published results on that. But probably the easiest and simplest proof of the fact that a graph, a complete graph, has the Miklos property is using So basically this is it. This is what I was just saying, that this gives you a lower bound. So once you can find that many, minimum degree many edge-independent perfect two matchings in a graph, then that implies a mathematical single property, and that's easy, relatively easy to find using induction in a complete graph. Having the previous tools, we found a couple of results which gave some results on some certain graphs, I mean about the vertex sign balance of the graphs, how big can it be, which are the graphs which have the mathematical single property. So for example, the second part of the theorem, the first theorem says that if you have a k-regular graph and k is very big, I mean it's almost as big as it can be. It's not n, but it's a little bit over 2 over n half. So you have a k-regular graph, then this one has the mathematical single property. So it's gives you another family of graphs which have it. And in general, about k-regular graphs, not assuming the volume of the regularity, the size of the regularity, still you can give one of can give a lower bound on the vertex sign balance. It's not as big as the minimum degree for the k-regular graph. The minimum degree is of course the same as the uniform degree. It's k, but at least it gives you that it's k half. The second theorem says that if you have to take the Cartesian product of two graphs and one has the mathematical single property, the other then the Cartesian product will also have the mathematical single property. And there are a couple of other statements, but still it leaves open the question whether we can decide or not, in general, whether a graph has the mathematical single property, and part of the question is answered by this theorem. This Dezso Miklos is not this Dezso Miklos, but this is the son of him. We got it together with one of the other students, and basically it gives that this property is empty complete, so it's not really, there's no big hope that we can find some good characterization of graphs with the mathematical single property. So in general, and we are using the earlier result of these 5 authors. So I mean, our result is not very powerful. The previous one is very powerful, and it's not very difficult to reach to the second theorem from the one. So that basically is the status of the vertex sign balance as far as we know right now. And then I have a few words about the vertex sign balance of the hypergraphs. As I mentioned, of course, I mean, in general, that is the most interesting question, and as I mentioned, it can be defined exactly the same way. You assign weights to the vertices of a hypergraph, and you want to see the minimum number of, I mean, the total sum positive, and you want to find the minimum number of positive edges under all possible weight assignments. So that is the vertex sign balance of the hypergraph, and again, if this weight assign, if this minimum number is as bad as it can be, I mean it's equal to the minimum degree, it cannot be bigger than the minimum degree, then the hypergraph is supposed to have the mathematical single property according to the original definition of that notion. I copied here at the bottom of this page the theorem which was stated about the graphs, and the top theorem is just basically the equivalence of statement number 1 and number 4 for t-uniform hypergraphs. So if you have a t-uniform hypergraph or k-uniform hypergraph, if you want, then it's this, I mean, the decision, the fact whether the graph has a positive vertex sign balance is can be decided exactly the same way as for the graph. You take the fractional matching number, and if the fractional matching number is as big as it can be, then then the vertex sign balance is at least 1, otherwise it's 0. Now, unfortunately, the hypergraph version of this theorem is not known. Actually, it's not completely true. So the middle two statements cannot be generalized for hypergraphs. So therefore, this kind of edge removal lemma which we have for the graphs is not available for hypergraphs. But definitely, the conclusion of I mean, part of the conclusion what we got for the graphs is also true for the hypergraphs. Unfortunately, you cannot prove, and probably it's not true that this the existence of delta edge independent perfect matchings, perfect C matchings for some certain constant would be equivalent to the LMS property, but at least definitely it implies. If you just forget anything what basically more or less what I told about the problem, of course keeping the definitions, then probably everybody can prove it in about 5 minutes that this is a sufficient condition to prove the mechanical single property. And this can be a powerful tool. As I said, this tool worked in the case of the complete graphs. We tried to apply this tool for the complete three uniform hypergraphs. Have not succeeded yet, but I am not giving it complete graphs, so probably it will work. Of course, you have to be clever how to find those edge independent perfect symmetries. So I have some time, so I go to the dual of the vertex sign balance. Again, it doesn't take too much time once you get from the mechanical single property to vertex sign balance, then to move forward and take the other way of weighting of a hypergraph. So now instead of weighting the vertices, you want to weight the edges, and now a vertex will inherit the weights in the way that all the edges containing that, I mean the weights of the edges containing that particular vertex will be signed up. So you can do the same. You want to somehow assign weights to the edges which are altogether positive. The total sum is positive, and now you want to minimize over all the possible weights, over all possible weightings of this type, the number of positive weight vertices. So the question is how small can it be? And this is a big surprise that it can also be 0 even for certain hypergraphs. And clearly, like the minimum degree was an upper bound, in this case the minimum size of a vertex, the minimum size of the edges, now that's a history of the vertex, so there's the minimum size of the edges, is the upper bound on the edge sign balance. Again, what you can do is you even one big, you choose a minimum edge, you assign a big positive number, all the edges get negative, all the others get negative number. So a vertex to inherit a positive sum must be contained in this minimum edge, so that many vertices can be in the worst case with positive weight. But again, it's not very difficult to find some examples, some hypergraphs when this number goes down to 0. And also, it's quite clear that the vertex sign balance and the edge sign balance are dual properties. So edge sign balance of a hypergraph is equal to the vertex sign balance of the dual of it. So in that sense, of course, it makes no sense to introduce the edge sign balance, because once you know everything about the vertex sign balance, you know everything about the edge sign balance. Fortunately, we don't know everything about the vertex sign balance, so it makes sense to investigate that. The cases which are somehow can be tackled are very different for the two different notions. So for example, the edge sign balance of a graph is trivial. That could be an easy homework problem for the first combinatorics course to prove that for a graph is between 1 and 2, it cannot be 0. Actually, it's true that for a uniform hypergraph, the edge-side balance is at least 1. So for a graph which is a two uniform hypergraph, it's at least 1. If you want to find a counterexample, you have to include the edges of different sizes. And since the uniform size of the edges is 2, therefore 2 is an upper bound, so it's between 1 and 2, and it's 2 only if and only if the graph is bipartite. So it's really very easy application. Probably once you get to the bipartite graph section in the graph theory class, then you can introduce this problem. Then the next step was to try to find out as much as possible about the edge-side balance of the three uniform hypergraphs. Once you know everything about the two uniform hypergraphs, and as a three uniform hypergraph is uniform, so the minimum of the edge-side balance is 1, the maximum is 3. So the question is, which are the three uniform hypergraphs with edge-side balance 1, 2, and 3. And then this conjecture turned out to be too difficult, so it's still open. Whether it's true or not. Clearly, if you find vertex independent perfect 2 coverings, then similar to the previous statement when we found the matchings, so the coverings, existence of many independent coverings will imply a lower bound on the edge-side balance. So clearly the maximum is a lower bound on the edge-side balance. The question is if it's optimal or not. And then for regular hypergraphs, the generalized version of the statement which we have for the graphs, the edge-side balance is at least 1 if and only if the graph has a perfect 2 cover is true, but in general, for any arbitrary hypergraph, when the edges might have different sizes, we don't know if it's true or not. Probably it's true. Thank you.
Okay, questions? Comments?
So, first question is, do you know whether this Miklos sinking conjecture is true for 3 uniform hypergraphs, for 3 uniform or for small uniform hypergraphs?
For 3 uniform.
So for graphs it is known.
Yes, for 3 uniform. Yeah. Yes, my guess is that yes, it's proven for 3 uniform hypergraphs. It's proven for graphs, uniform hypergraphs, and it's proven for 3 uniform hypergraphs. Yes, it's. And that's it. That's the end of the story. I mean, not for any other.
And personally, would you believe in Blinovsky's proof, or like, what do you think?
I believe the statements. I believe the statement, but as I said, I have no idea about the validity of the proof because it wouldn't. It's not like I found a gap which I don't understand might or might not be true. I was not able to step from the very first page to the second one, and again not because of the machinery, but because of using notations which were not defined in the paper. Somebody has to be very clever to figure out what are those parameters he is working with.
More questions? Okay, let us thank